Hi, my name is Toby O'Geen. I'm a professor and soil resource specialist in cooperative extension. And today I'm going to give you a brief overview of streamflow generation in California rangelands. And my expertise is in soil-landscape relationships, and so the perspective I'm sharing with you today is really from a soils perspective and a soil geography perspective on how the nature and properties of soil influence saturation of landscapes and how the saturation of landscapes feeds streamflow. We studied soils in Yuba County in the Sierra Nevada foothill region, and this is a common soil that you would expect to find in that area. It has a very permeable upper layer, a slightly less permeable clayey layer, and then what we call a clay pan below here at about 60 centimeters, between 60 and 50 centimeters. And that layer perches water above it. It's very slowly permeable. And so what happens is saturation builds upwards, feeding these permeable layers, which then conduct water down the landscape. These soils are highly variable across the catchment, and we tried to study their geography in this experimental catchment, which is located down here in the lower part of your slide. We placed sensors all over the catchment to measure water content through time. We collected water at a location right here at different layers in the soil and measured the flow rate of the water coming out of those horizons. And we also measured stream flow and tried to understand the timing of streamflow generation relative to the timing of subsurface lateral flow in these different soil layers. This is a hydrograph here showing you how rainfall here at the top of the graph corresponds with streamflow down at the bottom of the graph. And what you see is that it takes a little bit of rainfall first to generate streamflow. About 7.5 inches of rain has to fall to fill up the soils before streamflow will actually occur. And what's happening here is the soils are recharging from their summer deficit. And then, after about 7.5 inches of rain, you start to see very flashy episodic events of streamflow, indicated here at the bottom of the graph. These flashy storms are characteristic of ephemeral streams located all over and across California rangeland systems. And so our goal was try to connect the timing of subsurface lateral flow with stream flow so that we could better understand how these landscapes generate stream flow and how that might influence water quality. What we found is that the upper layers, the A and B horizon, which we call a biomantle, are the highly permeable layers, responsible for about 73% of the stream flow during storm events. The clayey layer just above the clay pan only supplied about 17% of stream flow, and that's because it's more slowly permeable. Layers within and below the clay pan were responsible for much lower stream flow. And so what's happening is water is falling on the soil surface, infiltrating down through the profile, hitting that clay pan, saturating above it, saturating upwards. When that water hits these permeable layers, the A and B horizons, gravitational flow occurs and water is quickly released downslope. The significance of this is that we can understand where on the landscape stream flow is being generated from, possibly targeting management opportunities. But also we can understand, based on rainfall and knowledge of soils and their water holding capacity, at certain times of rainfall events, certain types of storm events, we can get some insight into the water quality. For example, if water is being supplied from the uppermost horizons, we could surmise that the quality of that water might be lower than, say, lower in the profile where there's fewer nutrients. And that's kind of what this graph shows here. The dark blue is showing you dissolved organic carbon concentration, which is a water quality contaminant, in the upper layers, the A and B horizon, and in the lower layers. And you can see that it decreases with depth. And we see the same concentration of dissolved organic carbon in stream flow, base flow, rising limb, peak flow, falling limb, and base flow again. And what you can see here is that the higher stream flows, the peak flow, rising limb, and falling limb, have concentrations that are similar to the upper parts of the profile. And the base flow is more of an integration or an average of all of these layers. So understanding how saturated soils are and to what depth can give us some insight into the water quality.
For more information on this topic, we invite you to view a more in-depth presentation that provides science-based insights and conclusions. You can find this and other ranch water quality presentations on the UC Rangelands website, and look for the Water Quality Information Hub or direct your web browser to the URL shown on this slide.